Hello, my name is Vincent, and I'm going to present you a paper, Efficient Precision Control in Object Detection Models for Enhanced and Reliable Ovarian Follicle Counting. So, our task is to count the number of follicles inside some ovaries, here the image on the left, and you have the follicles on the right inside of the slide. And we have three types of follicles to count, primordial in red, primary in green, and secondary in blue. So our objective is to detect as many follicles as possible, but we also want to solve this standard precision recall trade-off by while giving some guarantee on the precision. So we have three main contributions in our paper. The first one is a new open source dataset with more than 600 images, an object detection model to detect and count the number of follicles, and also a decision rule to bypass the standard precision recall trade-off. So to show you what we did in our paper, so we have this standard precision curve according to the threshold, and what we want to do is to control this precision at level P0, which means that we want that on the test set, we want to have a high probability that our precision will be higher than this threshold. A naive way of choosing the threshold for the object detector is to take this naive threshold, which is basically the intersection between P0 and the precision curve. However, this methodology doesn't give you any guarantee on your precision on your test set. So what we do is we follow a multiple test methodology where we define a set of threshold, lambda j, and for each of them, we run a hypothesis testing. With H0, the precision is lower than P0, and H1, the precision is higher. From this test, we'll have some valid p-values, which mean tests which reject the null hypothesis, and we will compare our p-values not to delta, but to delta divided by n, because we're in some multiple test procedure, we have to penalize our p-values. So that's what we divided by n. So this is what we call a bound-theory correction, but there are also other type of corrections such as the fixed sequence testing or the sequential graphical testing, which we also use in our paper. So based on this methodology, we are able to find the optimal threshold lambda star, which gives us some p lambda star precision. And we have the following guarantee. We know that with a probability 1 minus delta, that our precision p lambda star will be higher than p0. This is a result from a paper from Angelopoulos et al. Called Lanza test, and this is the methodology that presented in the paper. One drawback of this methodology is that once you have chosen lambda star, you are stuck in this standard precision recall trade-off, and you won't be able to improve your recall. So what we propose is to use some biological information. Here in our example, in our dataset, we know that the follicles are located on the border of the ovaries and not in the center. So we'll create a new indices for our predictions, di, which is the depth, which is equal to 0 if the prediction is on the border of the ovary, and equal to 1 if it is in the center. With this threshold, we run a multi-criteria precision control. So instead of choosing lambda star, we'll choose a couple lambda star mu star being the set of threshold for the depth. And by applying the same Lanza test procedure, we'll be able to achieve the same precision control as with the standard one criteria Lanza test. However, we don't always have access to this kind of biological information. That's why we also propose a methodology to first learn to classify your bounding boxes, and then to give a false detection score to your predictions to have this two-dimensional precision, which will be precision which is defined by lambda and mu. So in our result, we have shown that for two different models, efficient and Olivier, we are able to improve the F1 score of the naive Lanza test procedure with only one criteria. And we are also able to control the precision on our test set, which is the theory, only the theory. We also show that our methodology here in orange is, and in blue also for yellow V8, is even better than the standard way and the naive way of choosing a threshold without this multi-testing procedure. So to conclude, in this paper, we have open source a new dataset with more than 600 images. And we have also a very good follicle detector. And we are not just, we have also some model-agnostic procedure to improve the performance of this model without having to retraining it. And we have also the possibility to use some auxiliary model to make our methodology even more general.